Welcome to this video series on how to do quantum mechanics using programming. A lot of the existing quantum mechanics courses and videos rely heavily on analytical calculations to get the sort of intuition, and the goal of this video series is that we're going to use only programming as a tool in order to gain the same kind of intuition, meaning there will be no long analytical calculations, only programming. And by the end of that, we're going to create a lot of animations and visualizations. So for instance, here you can see a wave function, a quantum mechanical wave function hitting a potential, and then part of that wave function tunneling through the obstacle. Now, right now, this video or that video that I just showed you might not be very clear what it means and so forth, but the idea is we're going to build up to that point where we understand what that video shows us and also how we can do calculations on that simulation. So the goal of this video is not going to be too heavy on the programming. We're going to cover some of the historical context for why quantum mechanics became the way it is with the Schrödinger equation in particular. And then I'm going to show you an outline for this whole video series that I have planned. And then at the end, I'm going to give you an exercise for you to try to do before the next video. And I highly recommend that you actually try to solve the exercises between each videos, because when you're trying to solve problems, that's when your mind is really at work and learning. So yeah, and apart from that, I hope you will like this video, subscribe, and share it with your friends, a comment, so that it can be spread to other people if you think if this was interesting. So the sort of physics pre-1900s were a situation where people thought, or physicists thought, that the world was composed of essentially two types of things. There were particles and waves. So particles were like you have balls interacting or planets, and then you had waves. And we knew that water was a wave, and we knew that sound was a wave. And then there was a question about light, because Newton thought that light was a particle. But then in 1802, Young did his famous double split experiment, showing that when you pass light through a double slit, he discovered that you got this interference pattern, which is a phenomenon that is associated with waves, not particles. And then in 1897, Thomson found that the electron existed, or he sort of proved that the electron existed, and showed that the electron had like a discrete charge, like a charge associated with it, which supports the idea that the electron is a particle. And so people were sort of happy putting these things into like these two boxes. But then the photoelectric effect was discovered, and Einstein was able to explain this photoelectric effect by saying that, well, maybe light is not actually a wave, it's a particle, a photon, and its energy is given by the frequency multiplied by h. And so this was one of the first indications that maybe the sort of simple division into like particles and waves wasn't completely correct. And then in 1853, the hydrogen emission was discovered, and Bohr was able to explain this in 1913 using his atomic model, where the electron was allowed to sit on only like a couple of very defined places. Only a certain number of states were available to the electron. Now, these things all led de Broglie in 1924 to suspect that maybe the electron could actually be a wave, and in fact, all matter could actually be waves. And he suggested this relation of like how the wavelength is related to the momentum of a particle in order to make sense of these results. Now, it's not completely given why does it make sense to say that if if the electron can be in one of these states, why does that support the notion that it's a wave? And I wanted to, for this first video, I wanted to go to programming and show you how the idea of waves can support the idea that things can exist only in certain states. So what I have here is a Google Colab environment, and I have already installed Comfit. So the course that all the programming that I'm going to be doing in this course is based on this computational field theory library that I developed after finishing my PhD in physics. And we're going to use that in order to simulate the partial differential equations that we need to do to simulate. So we're going to start with the wave equation. So the wave equation is a differential equation which tells how waves behave. It's a wave equation. So if I write it up, it's this, right? So the spatial derivative of psi is equal to c squared times the Laplacian of psi. So here, I'm just going to double check that this is actually correct. I don't have any minus mistakes. Yes, so d squared over c. Yeah, so this is the wave equation. Now I have implemented this wave equation in Comfit. Now for the first video, I'm not going to be asking you to do a lot of programming. I'm just going to show you how it works. And then as we go into quantum mechanics, then I'm going to ask you to also do some programming. But for the first part, I'm just going to show you how this can look. So what I'm doing here in this script here is that I'm using this library Comfit to set up a system which will essentially evolve the wave equation. And the important part here is that in this region here, I'm setting up this differential equation here. It's not important for this first video. I just want you to show what it looks. So what I'm doing in this sort of part here is that I'm creating an object which is called which is an object of this wave equation class. And then I am creating an initial state, which is a Gaussian. So if we go back to this figure, what I'm doing here is that I'm essentially doing a wave equation simulation in one dimension. And I'm starting with a line like this. And then I'm changing this initial condition to be just a Gaussian function, and I'm going to look at how this Gaussian function evolves in time. And so what I'm doing here is that I'm creating the system. I'm saying that it's a one-dimensional system. The velocity of sound on the string is 1, and then I've chosen a time interval of 0.005. I've created my initial state, which is a Gaussian, at position 75 of 100 with 5 and top 1, and then I go into this loop here where I evolve the system for 200 time steps. I plot the field, and then I save the plot. And then by the end, I take all those plots that I made and make an animation GIF. And if you're using Colab, then you can find the animation that's being produced on this left-hand side here. So if I double-click the result of this, you can see that this is how this initial wave function looked, right? So I started with a Gaussian at 75, and the initial Gaussian sort of moved to both sides. And then since it's periodic boundary conditions, it moved past the edge and then reappeared on the left-hand side and then met its own, the other side of itself, and then got constructive interference over here. Now, yes. So this is with periodic boundary conditions, right? So here the wave is going through here and moving to the left. Now, I can change the boundary conditions. so that instead of being periodic, I can force the endpoints to be 0. And the way that I do that is by essentially in this function called evolve, I set what I think the field should be at 0 to be 0. And that's essentially going to fix the value of the field at this location and that location. And so I'm going to update the evolve method. And if I now run the simulation, the initial Gaussian is no longer going to move through the edge of the system. It's going to meet the edge and then be reflected, as we'll see. So here you can see how it's producing all of these plots, and which are in the end going to be combined into a animation. Okay, so here we have the plot with the 0 boundary conditions. So here you can see that instead of this initial wave function, which starts here, instead of going through the edge, it's reflected on the edge, and it turns the amplitude upside down, and then it meets the other wave that's gone here. Now, what's special about this situation where we have fixed boundary conditions is that we can see that we get a particular set of states which are called eigenstates. And so the eigenstates are essentially going to be sinus waves, which goes from 0 and over to 0 again. And it's given by this expression here. I'm not going to go through this in detail. I'm just going to show you what the 0 eigenstate looks like. So here I'm creating a function which takes in the system and also a number n, and it's going to return what I call the nth eigenstate of the wave equation. So here I'm setting the initial state to the first eigenstate, and then I'm plotting that field. So here you can see what the first eigenstate of the wave equation looks like. And if I evolve this wave equation in time, so here you can see it's evolving, it's going to evolve right. So here you can see how the first eigenstate evolves, hopefully. Right. So here you can see how the first eigenstate evolves. So essentially, it's like this wave that goes up and down, but it sort of has the same position. I can also make the second eigenstate and look at how that evolves by changing the n in the eigenstate function to 2, and then also 3, and then also 4. Now, I should say that these simulations that I'm running here, they're not very stable, because I've just created this very quickly, and so you can see that after the sort of first iteration, we get this sort of squiggly lines on the function, which are essentially going to blow up in the end. So there are smarter ways to implement the wave equation. I just wanted to show you essentially how it looks. Right. So this was the first eigenstates. So it's sort of this whole sinus function here. Now for the second eigenstate, the sign is the n is equal to 2, and that results in this kind of situation here, where we have this double peak and trough situation going. But always the endpoints are always 0. And then if I go to the third eigenstate, You can probably guess how it's going to look. It's going to look like a peak and then a trough and then a peak, and that's going to evolve back and forth. Right. So here you can see how the third eigenstate sort of bounces up and down. And of course, here is the fourth eigenstate. So then you have like 4 peaks and troughs moving. Now, the point of all this is to show that the reason that this idea of the electron being a wave makes sense is that when you have something that's a wave with a given boundary condition, then no longer are every state available to the system. So for instance, for the string, since the boundary conditions are fixed like this, it means that the wave that sort of starts here and then goes somewhere and ends here is no longer permitted from the system. So a wave with fixed boundary conditions or defined boundary conditions is going to limit what states the system is allowed to be in, which is essentially what Bohr was saying when he said that the electron can only be in one of these defined states. So in music, for instance, this fact appears when you play a string on a guitar, for instance. Then you get this very nice sound, and the reason that you get this nice sound is because the fact the string is fixed at the edges means that only certain motions or certain states of the strings are allowed, and those are the harmonics, which sounds very nice to our ears, for instance. So, based on his idea, Schrödinger in 1926 came up with this wave equation for this supposed wave for the electron. And the goal of this video series is essentially that we're going to get to know the wave function. What is it? How do we plot it? How do we program it? And then we're going to implement the Schrödinger equation and see how these wave functions interact in some of the interesting cases. So the goal of this series, so now I'm on to the next part where I explain the goal of the series, is to get to know the wave function. We're going to look at what it means and how to calculate observables, because of course the question is the wave function something we can observe? The answer is no, but there are still things we can derive from the wave function, such as the expected position of a particle or its momentum or things like that. And so we're going to look at how to calculate observables. Then we're going to look at the uncertainty principle, and then look at how to view the wave function from the momentum representation. And I'm going to explain what that is. So this is the number of the video in the series, 2, 3, 4, 5, 6. And then once we've gotten to know the wave function, we're going to get to know the Schrödinger equation. And so we're going to start in one dimension by looking at free states, which is where we have no external potential, then bound states. I'm going to look at these 3 examples here. And then we're going to move on to 2 dimensions, and we're going to repeat the same process, looking at the properties of psi. And in particular, in 2 dimensions, the new thing that we get with the wave function is the angular momentum. So we're going to look at how to calculate the expectation value for the angular momentum from psi. And then we're going to go through the same thing again. We're going to look at free states and then different types of bound states. And in particular, yes, so both for the 1D case and the 2D case, we're going to look at quantum tunneling. But for the 2D case, we're also going to look at the double slit experiment and how we can simulate that on a computer. And also we're going to look at diffraction. And then lastly, we're going to move to 3 dimensions, and we're going to repeat the same thing. We're going to look at the wave function. How do we interpret it now? How do we plot it, etc.? And then we're going to look at free states and then bound states. And by the end, we're going to look at the hydrogen atom and the orbitals of the hydrogen atom. So that is the first video in the series. And my first exercise for you who is watching this video is for you to try to figure out what is the square root of -1, and also how do you calculate, I'm going to add this now, how do you calculate with the square root of -1 in Python? So those are the two exercises. I highly recommend that you try to do them. And if you have, then I will see you in the next video.